All right, so today I'm going to be covering properties of integrals, of the definite integral. That next video, I can kind of springboard off of this video and, start with the first fundamental theorem of calculus, right? So you should recall what a Riemann integral is. I defined it for you, right? And all of that stuff I defined in the previous video. So if you haven't watched that, go check it out. So I end off with this criterion, okay? And I showed why it's true. Now we're going to use it, all right? And we're going to satisfy it. And this is our theorem. Now it's a weaker version, right? But I'll explain the full version. I'll only prove this one though. And that is that if f is a continuous and monotonic function over a closed and compact interval, interval a comma b with the specific partition, this one, then right? F is Riemann integrable. It's just saying that continuous and monotonic functions are integrable, and we can prove it. And first, we're going to use this criterion. So we're going to fix epsilon to be greater than 0 and assume F is increasing, right, without loss of any generality. Then we have this, right, this difference between the upper and lower, which we know is just this, right? This is our equivalent form. I showed how this is true, right? This is the upper definition, and this is the lower over a standard partition. And the reason why this works, by the way, because the supremum and the infimum are just located at the right and left endpoints respectively. Um, because f is increasing, right? So f is increasing. So um this supremum is just the right endpoint, and this infimum is the left endpoint. Um, And so we're going to factor out a b minus a and use the linearity of sums to get this. But this is a telescoping series, and it telescopes to just f of b minus f of a, less than epsilon, right? Now this is implied by n, right? We're going to manipulate n to be this expression, this monster. But we were just saying that if we can find, an n so that, or partition, standard partition, but we found it. We just need to pick an n, right? I guess you could just say the ceiling function plus one, I don't know. But I mean, it should be obvious that, okay, we can find the n, right? That such that, the n is greater than this. So that's our proof. And in actually in theory we can prove, but I'm not going to. It's far beyond the scope of this course, that this theorem is true for all bounded functions with countably many non-essential discontinuities. Obviously, if it's an essential discontinuity, it's not bounded. But if it's a point discontinuity or a jump discontinuity, and it's countably many, right? Even if it's infinite, so long as it's countably many, I'm not going to go on the whole infinite rant though. It is integrable. Now, here's where things get interesting. If we know a function is integrable, which is literally 100% of the time in this course, right? We're going to assume the function is integrable, right? If f is defined and monotonic and integrable, then the integral, right, which is a real number, is just equal to the limit of the upper and lower sums as n approaches infinity. As we take more and more subintervals, as our approximations get better and better, that's the same thing as what our integral originally was, assuming it's differentiable. And here's a quick remark. Now we can compute integrals, right? Noticing the upper sum is less than or equal to every other tagged sum we could possibly find is less than or equal to the lower sum, right? That's how we define the upper and lower. And if we take the limits, maybe you could visualize that, we have the upper sum is less than or equal to, I don't know, the left point Riemann is less than or equal, for example, right? Right point Riemann less than or equal to midpoint Riemann, I don't know, right? Less than or equal to lower, right? But this limit is equal to this limit. The rest by squeeze theorem will just be squeezed in between. So then basically saying, right, we're going to choose for convenience our right endpoint, right Riemann sum, right? This integral is just equal to, assuming the function is integrable, the limit as n approaches positive infinity of the sum from I equals 1 to n of f of x sub I, right? F of x sub I is our right endpoint on the interval, times b minus a over n, which is our delta x. It's the length of the interval, sorry. So here's our full notation, right? Ignore kind of this like purple thing, I don't know. But we have the integral from a to b of f of x dx. F of x is our function inside. It's called the integrand. A is the lower limit of integration and B is the upper limit of integration. Dx is technically nothing. It's just a symbol that it demonstrates what variable we're differentiating in respect to. Similar like the dx in differentiation, it just tells us what variable it's in respect to. Now, very loosely, right? This is the Busey notation at its limits, right? We can't prove anything using this. But in a loose way, right? We can look at this S as an elongated F. We can look at this integral as an elongated F. So it's a sum. What is it a sum of? Well, it's adding infinitely small widths dx times the height f of x, right? So we're having these rectangles dx times f of x, and we're adding them up infinitely many times over the interval a comma b. That is what we're doing. That's what an integral is. It's not what an integral actually is, but I mean, it's very loosely speaking. So whenever you have the sum, so this is really helpful, really useful to think about in applied context in this way, like when you're dealing with work. But you could definitely prove it, right? This is just an intuition behind it. So here's an example. We're gonna evaluate this integral, right? And we're gonna use the limit definition. So first we need to figure out what x sub I is, all right? Our x sub I is always gonna be an a, so -1, plus I times b minus a over n. B minus a is 3 over n, right? So we're going to set it up as this limit, and we're going to solve. So the limit as n approaches positive infinity times what? The sum I equals 1 to n of f of x sub I. So x sub I is this. The function is x squared plus 1. So we're going to plug in anywhere we see an x, right? We're going to plug in a -1 plus I times 3 over n squared plus 1. So that's our f of x sub I times 3 over n. And we can evaluate this limit, right? Hopefully you remember how to do this. I explained how to do this sort of in summations. So for that reason, I will leave the rest to you. But the most important part of this all is, and by the way, these two cancel out, is to do this. All right. This is the most important part of it all. Okay. To get these set up. The rest, I mean, you should know how to evaluate it. I'm not going to go over that. But the rest is just limit, in limits and sums. But the setup is the most important part. So hopefully you can get that. Now we have linearity of integration. So sums are linear, right? Linear operators. Limits are linear operators. Derivatives are linear operators. So linearity of integration is pretty simple. Works like linearity of anything else. We have a constant times a function plus a constant times another function. We could just get this. All right. Hopefully you see that and it just makes sense. We can factor out a constant from the integral, right? And we can split the sum. Associativity, right? If we're taking the area from a to b of f of x dx, right? Because that's what an integral is, by the way. I talked about this in the other sums video, um, which unfortunately isn't posted by the time I'm posting this one, but hopefully I will post it. Right. That's an integral is the area from a to b. And for adding up that area, it's the same as adding the area from a to c, which is c is the point in the middle, plus the area from c to b. That one should be obvious as well. And now we're going to define orientation of integrals, right? If we want to, for a less than or equal to b, it obviously makes sense to have the lower limit right here and upper limit here. And what if we do that except in the other way? B being the bigger number on the bottom and A being the smaller number on the top. Well, we define this just to be the negative of this integral. What are we saying? Right here, if we are going from left to right, we get a positive area because it's above the x-axis, right? But if we go on the opposite side, we get orientation, we're going to get a negative sign. Think about it like if you're, if you're going forward, if you have positive velocity, right? And you have negative change in time is going to have a negative displacement. I guess that's not like the best example. It's not very specific in this instance, but it should hopefully have you understanding orientation and just taking the negative. So you can switch the two limits and just take a negative, and it's the same thing. So if we evaluate this from A to the A, obviously we can swap A to A and get the same thing and get negative. The only way anything is equal to the negative of itself is if the thing itself is zero, right? That should be apparent, and if not, you could just do algebra and get it zero. Pretty simple. Next is translational invariance, which is again identical to summations. We can add a number to a function to the argument and then subtract it from the upper and lower limits of summation, and we get the same thing. And scaling invariance. We can multiply the inside by any constant k, and then we multiply the outside by the same constant and do the opposite. So divide the upper and lower limit. Okay? So remember that. Finally, it's not finally, by the way, monotonicity of integral. Um, that is to say, if um if for all x in the interval f is greater than or equal to g, so f is a function above g, then the area, right, of f is going to be greater than or equal to g, right? Should again also be another pretty obvious one. Of course, if a function's outputs are all above another function, then the integral is also going to be above. Another not necessarily obvious one, but provable, is that if a function is Riemann integrable, then its absolute value is also Riemann integrable. That's literally it. I'm not gonna explain much. That's it. Okay. Yeah. If a function is Riemann integrable, its absolute value is also Riemann integrable. And I mean, it makes sense, right? There's nothing confusing about it. The absolute value, right? We'll see when we get to rectilinear motion. It just takes anything that's below the x-axis and it reflects it above. There's no reason why it causes it to not be Riemann integrable. Finally, is that um, this one, which I'll explain, is that the absolute value of an integral is less than or equal to the integral of the absolute value. Why is this apparent? Well, what we're doing is that we're taking an overall area, right, of any function and just making it positive, that's the left side, is obviously never greater than, it's always less than or equal to, adding up only the positive areas. And you might be able to relate this to triangle inequality. Right? If we take these intervals, right, where f is positive and where it becomes negative, right, we add up those areas, we can either be doing a plus or minus b plus or minus c or plus or minus d or whatever, how many we have. This is always going to be less than or equal to just taking the absolute value, right, ignoring the negative and only adding up the positives. So hopefully another obvious one. So none of these should really be super hard to memorize. They're super hard to understand. They're all intuitive. Right, and I'll try to make the other sums video, right, because it provides not necessary context, but some context for this video. But this is the important one for the next video, which is the first one on the theorem of calculus. So good luck studying, and I know you do well as long as you practice.